Good evening, AP Physics students. Mr. Carson coming at you here along with guest lecturer Darth Vader. And we're going to be working on the photoelectric effect today. Great way to enter into the quantum realm, the realm of physics where things aren't always the way they appear, and particles are waves, and waves are particles, and there's a duality here, and things get weird, and people don't believe that God plays dice with the universe, and all sorts of other good stuff. So anyway, let's talk photoelectric effect, right? This is what makes solar panels work. This is what makes infrared sensors work. This is how your remote control works. So much good stuff going on here. So in the photoelectric effect, I have a metal. Usually it's a metal. And a photon comes in, hits the metal, and removes an electron. Okay? This is the equation here. K max, the maximum kinetic energy at which the electron is removed, is equal to the energy of the photon, of the incoming photon. Remember, Planck's quantum hypothesis said that energy of light photons are quantized, and they're equal to Planck's constants times the frequency of the photon, minus the work function, where here the work function is the amount of energy it takes to remove an electron from the metal. So if you think about it, this is really just a statement of conservation of energy. The energy in has to equal, how much energy it takes to remove the electron, and then this would be the leftover kinetic energy from there. Also, a little reminder here, Planck's constant is 6.63 times 10 to the minus 34th joule seconds. Okay. Guest lecturer Darth Vader, what do you think of the lecture so far?
Most impressive.
Oh, well, I'm glad you like it. I'm glad you like it. Okay, a couple other reminders here. Remember that the speed of light, or the speed at which light moves, is equal to the frequency of light times the wavelength of light. That's something we'll want to keep in mind. Also, would just like to point out to you that on your equation sheet here, while the book uses omega naught for the work function of the metal, your AP equation sheet uses the Greek letter phi to represent the work function. So just be aware of that. Also, Planck's constant, while it's in joule seconds, it is also listed on your table of information, and it is listed in electron volt seconds, and also the quantity H times C, which gets used a lot, is listed on there. Okay? Let's see. Also keep in mind that when it comes to electromagnetic waves like light, okay, the longest wavelength, which this problem asks about, the longest wavelength corresponds to the smallest frequency. And that also means the least amount of energy, right? Frequency and energy are directly proportional. So the larger the frequency, the larger the energy, the smaller the frequency, the smaller the energy. And as wavelengths get larger, energy gets less. Doesn't that sound right, Darth Vader?
Yes.
Oh, well, good, all right. Well, I better get going here, otherwise I won't finish the problem here in the 10 minutes I have.
I find your lack of faith disturbing.
Oh, don't worry, I will finish. We'll finish for sure, Mr. Vader. So have no fear. Okay, we're gonna put you right up here and continue on here. Here is what we know from this problem. It wants us to find the longest wavelength that will still eject electrons from this metal that has a work function of 3.1 electron volts. So basically what we want to know is we want to know when K max is 0. That is, the photon has just enough energy to remove the electron from the surface, but not any extra energy. Okay? So if I plug in 0 here in this equation, all right, then what I find is I just get HF is equal to omega naught. In other words, the energy of the incoming photon will just equal the work function. Now, if I take this equation here, okay, and rearrange it, remember that F is equal to C over lambda, rearranging this equation. So I'm going to get HC over lambda is equal to omega naught, where here this lambda represents the longest wavelength or least energy wavelength that would still be able to remove this electron. So we are closing in on the solution now.
I had you now.
That's right, we're almost done.
No.
Yeah, we're almost done.
No.
Yes, we are.
Yes.
Okay, so if we rearrange this equation, we find that the longest wavelength that will still eject electrons from this metal surface would be Hc over the work function. Now, in this equation, since this equation all deals with energy, there are two units we've used to discuss energy: joules and electron volts. Now, sometimes it's easier to do problems in electron volts than it is with joules. For instance, in this problem, I'm going to go ahead and just use Planck's constant in electron volts here to solve this, okay? So I'm going to get here lambda is equal to Planck's constant in electron volts, or 4.14, times 10 to the minus 15th electron volt seconds, times 3 times 10 to the 8th, that's a times there, meters per second, divided by the work function and electron volts, which was 3.1 electron volts. Notice here that electron volts cancels, seconds cancel, and I get a wavelength that is in meters. And sometimes when dealing with quantum phenomenon, we'll just go ahead and write that wavelength in nanometers. So this is 701 nanometers, which puts it in the violet range of the spectrum. When looking at the electromagnetic spectrum, typically 400 nanometers to 700 nanometers, and this is visible light, I should say. Visible light, not the full electromagnetic spectrum. But this is usually the range of frequencies of wavelengths for the visible light. So that's the deal there.
I am altering the deal.
Okay, all right. So this is violet light, and this is red light. So if we shined violet light onto this metal surface, it would have enough energy to just barely eject those electrons there. Okay. If we shined red light on it, that would not be enough energy to eject those electrons. And if we shine something more energetic than violet lights, like X-rays, those electrons would come out very quickly. So there you go. I'm sorry I kind of rambled here a lot.
Apology accepted.
Okay, all right. But hope we had a good time, and nice work on doing your physics homework.
I had you now. The force is strong with this one.
All right. Nice work, physics students. We'll see you tomorrow.